Welcome. It's quite remarkable that so many people show up, even though the holiday season is about to start.
And the weather.
And the weather is, so that shows how popular some of our speakers are, and great intellectual attraction to hear your talks. We have 3 speakers today. I should mention that shortly after this is the last set of talks for this semester, and we will renew the talks on the 21st of January. So just mark it on your calendars if you're around to show up here 21st. You can sit here. After the talks end today, we will rearrange this room very quickly and have a party, a winter party. So everyone is invited to stay and socialize. So we have 3 speakers, and we'll start with the first.
I'm just here to introduce the speakers, so I'm extremely happy about the speakers we have today, because all of them are my dear colleagues and good collaborators. So the first speaker today is Debora Lancova, who is a PhD student at the beautiful city of Opava in Czech Republic. We're working together on a very fun project, accretion disks, and Debora will tell you more about this fascinating project.
Thank you, Maciek. First, I need to apologize. I'm a little bit sick, so maybe it will be a little bit shorter, and I can speak properly. So sorry for that. As Maciek said, I'm a PhD student from Silesian University. First, I just wanted to show where Opava actually is, because nobody knows it. It's so it's a small town in the borders of Poland and Czech Republic.
Which side is it on?
It's on a Czech side, actually, but it's like 3 kilometers to the border, so it's very close.
If you go for a jogging, you can easily go to Poland.
Yeah, it's a very nice place. So, and it's, as I said, it's a small historical town. We have a nice town hall, and this is our university building. So, this just.
What is the Whitehall Observatory?
Yeah, what is that Whitehall?
Whitehall Observatory, actually, it's our observatory we have. At the roof, it's a small observatory. They call it Whitehall because it's like.
Because he wanted a nice abbreviation.
Yes, it's one reason.
Nothing is coming out of it.
No, nothing is coming out of it. It's a name, and also because Professor Stuklik, the leader of the institute, is working a lot about these naked singularities, and so it's because of it. Also, we have a new planetarium, which has in some sense it has the highest resolution at the board these days. It's brand new. Someone will be definitely like better. For now, it's the best. Okay, a puffy disk. The motivation for doing it more than a year ago, when I first came here to visit Maciek, was to do a simulation, GRR MHD simulation of a thin accretion disk. To have a really thin disk, to have it with radiation, a global simulation, so we can study the stability of this disk. And the main reason was to see the variability, to see some traces of QPOs. It's very challenging to simulate a thin disk, because one needs a very high resolution, because the disk is so thin that in the equatorial plane you need a lot of cells to resolve the MRI correctly. Also, with radiation, you need the correct treatment of the radiation, because in the domain there are both optically thin and thick areas, so it's hard to do it. You need a 3D simulation to study the variability, so the resolution has to be very, very high. There are some simulation. I choose the. Yes, sorry.
Very naive question. What is a thin disk?
It will be in the next slide. Yes, basically a thin disk is the model of accretion disk around black hole, which is extremely geometrically thin. It's sub-Eddington. So
what is it mathematically to define
the height relative to the radius? The height is small relative to the radius.
And there's some expansion in that?
Yeah, you can do that expensive treatment. It is in literature known as Kluźniak-Kita solution upon the relativistic solution by, well, Page Thorne and other guys.
Okay.
It will be on next
Novikov and Thorne.
I missed. Thanks.
Okay. I choose some examples of existing simulation. There are some with radiation. For example, Bhupendra here did a simulation of, okay, it's not working, of a fin disk. Also, Matthew Lishka is not here, but he's now a postdoc in Harvard. He's doing a simulation of tilted fin disk without radiation. So, what is a fin disk? It's an analytical model. It's 1D model for accretion disk. It's dominated by the analytical model is dominated by the radiation pressure. So the matter inside the disk is very turbulent. It's driven by MRI, but the motion is almost Keplerian. The inner edge in the analytical model is in the innermost stable circular orbit, so an ISCO. We know it's a good agreement with observation. The fin disk has a thermal spectra, and it's radiating almost radial. The radiation is coming out earlier, there is no advection of radiation. So, one of the known simulation was done by Oleg Sondrovsky, who was a postdoc here as well. He published his results in 2016, and we based our work on his work. So we have his data, we use it to extend the simulation and do like a proper analysis of the results, because Oleg in his paper was mostly about the stability, the efficiency, and so on. But in this paper, one of the biggest problem with a fin disk, and it's the analytical model. It's that it's unstable. The instability causes it to collapse towards the equatorial plane very rapidly. So Oleg in this paper shown that if you have a magnetic field with a correct topology, the disk will be stable and it will be thin. So we used his work as a starting point. We use
what is it unstable to? What does it tend to do, the disk, if there are no magnetic fields?
So the problem is that the radiation cooling is more effective than the viscous heat. Yeah. So the radiation cooling is more effective, so it radiates away all the energy and collapses. There is nothing to hold it like stable. You need another pressure to add to the gas to keep it stable. And it's not Oleg's discovery. It was discussed before many times that the magnetic field can be a source of this additional pressure, and then you expect to have some magnetic field in a plasma around a black hole. So it's you can expect this could work. But what Oleg did in his paper was that he found the right setup for the simulation to So we used his code, Coral. Just some information about the code. One of the important property of the code is that it uses the M1 closure scheme. It's basically the way how you can treat the radiation. In the end, it's just saying you how you can write the radiation, the whole radiation stress energy tensor you need if you know only fluxes and the energy density. And this closure scheme is very good because it can solve the optically thin and thin region quite good. The initial state of our simulation looks like this. This is so we have a very huge torus far from the black hole. The inner edge is actually at 42 Rg. The outer edge is also the outer edge of our domain is at 500. The torus is okay. Thank you. Okay, the torus is treated by this at toroidal magnetic field where there are two counter-rotating and rotating loops inside the torus. So we start a simulation like this. Because there's radiation, there's a magnetic field. This is not a stable state, so the gas starts to accrete on the black hole, and it actually forms a very thin disk here in this region. I have to say that the simulation is the resolution, everything is set up. So half of the resolution of the whole domain, it goes like up here. It's a big, like half circle. And most of the half of the resolution is in this small area around the black hole, actually. And this is the only part of the simulation we analyze and we care of, and I will be showing you later pictures.
Are the loops magnetic fields?
Yes. And also the okay, sorry. So as I said, we have a high resolution, 320 to 32. We are not simulating the whole 3D. We are simulating a 90 degrees wedge because it's for our purposes it's fine. We can use it. There's a boundary condition, so. But we have 3D simulation, but only in this wedge. We know that we can resolve the MRI correctly because the quality parameters are high enough. We have 3 simulations. 2 were done by Oleg, and 1 was done by me. So the lowest accretion rate we can get from the simulation is 0.6 Eddington. We ran it for a very long time. It's just, for example, the newest simulation, the 0.6 Eddington took 8 million core hours on a supercomputer, which could be 900 years on a single computer. The simulations are very costly. But we obtain a nice kind of Polish supercomputer Prometheus, so we already obtained a second for next 2 years, so we have the computational time and we can do many new simulations. The grid is very it's so exponential. In the innermost parts, the cells are very small. It's because the disk is also very small in this part, so you have to be like this. Okay, this is the result of this model. So it's a free average data. It's so you can see this is I cut through the equatorial plane, which is here. This is from above to look at the equatorial plane. Yeah, you can see the disk. The gas is very turbulent. It's it's a density in a logarithmical scale. So you see most of the density is concentrated here around the equatorial plane. I will show better pictures later. But it doesn't look very thin. So we realize that we are not simulating a thin disk, that we have something which doesn't have an analytical model. We have we call this solution a puffy accretion disk, actually, because it is a little bit puffy. But this disk has a lot of common with both thin disk or another analytical model, slim disk. So there is a high density core which is very thin. Again, this is density in logarithmical scale, so there is almost nothing. But it's also optically thick, so the surface of the disk we can see is this white line, and you see it's in the end it's not thin, it's on the other hand very thin. And between the thin core and the photosphere here, there's this puffy region, which is low density, but it's very hot. There's a high temperature, and also it's strongly magnetized.
So is this the corona that emits X-rays or not? Is this the corona? Because
it's optically thick, so corona. The surface, the observable surface is the photosphere, so it's not a corona.
And what is the temperature? The inferior temperature? It's very high.
It's
the
very
X-rays.
Yes, it is. Yes. There's a, so we can see it's also very turbulent. This is a also the position of the photosphere is moving. Before I show this is a time average data over the whole 1500 DG run ahead. So, but you see it's very turbulent all the time. Another interesting property of the puffy disk is that it's advecting radiation, which thin disk is not doing. Here you can see the radiation fluxes and the radiation temperature, and you see that the vectors showing the radiation flux is going inside. So most of the radiation is actually goes into the black hole. Only from this area it's escaping to infinity. But if you look at, for example, 15 RG, radiation is going almost radial, but the radiation is coming from like more inside from the disk and then out. So it's advecting the radiation. Again, even it should be moving. It's not. Sorry for that. It works a while ago. So even the radiation flux is it's very turbulent. This is again a snapshot from the simulation. So even here you can see the turbulence. It's nice and smooth, but in the average data is nice. This is a plot of the momentum of the gas. So you see this, in the disk there's it's almost like in a thin disk when there is almost no movement of the gas, because it's moving very slowly towards the black hole. But in the puffy region, it's and the gas is moving into the black hole. There is also some kind of stagnation radius from which the gas is going to the black hole or escaping to infinity. In this funnel region, the matter is pushed away by the radiation, so it's moving quite fast. Again, it's turbulent when you look at the snapshot. Another property which is not typical for a thin disk, you can find this in a thin disk, is a super Keplerian area. It's a place where the gas is moving faster than with a velocity higher than Keplerian velocity. It's not so it's a little bit super Keplerian. The values are not very high, but it's sorry. But it's an interesting property, which is more similar to a thick torus, Polish donuts, and this kind of disk. As I said, the disk is stabilized by the magnetic field. You can see the magnetic field lines here. So the ratio of gas and radiation pressure to magnetic pressure in the disk itself is about 1. So, but there are this area which is much higher. It's close to the photosphere and close to the place where the magnetic field is changing its direction. The magnetic field in the funnel region is almost radial. It's nice and smooth. This is again average data. If we look at the time snapshot, we see that the magnetic field inside the disk, outside it's still very nice and smooth. Inside the disk is extremely turbulent. And another interesting property is that with the simulation with mass accretion rate 0.6, we see that most of the accretion is happening in this puffy region. So, if we look at the full domain, this is the red curve, it's everywhere. Everything is almost all the matter is going to the black hole in the area below the photosphere. But if we look in the green line, which is below the density scale high here in the actual fin disk. The mass accretion rate is going almost to zero, and because maybe we will see that with a lower mass accretion rate, it can actually be some backflow in this part of the disk. But most of the mass is going inside in this buffed region above the density scale high under the photosphere. So we also look at the alpha parameter. Computed as in a PENAS paper in 2012. We see that the alpha is not constant in the disk. It's this value up to 8 is about 0.01, but there is this high bump you can see, which is causing the gas to go in the innermost areas. What we are preparing now here is a paper on observational properties of puffy disk. Ramesh prepared nice spectra and nice images of puffy disk using his code, Heroic. And the most important is that instead of thin or slim disk, which are typically used for this luminosities, the puffy disk is much thicker. So the central part where most of the radiation is coming from is for higher inclination is shielded away. You can see it. So for low inclination, we can see the inner part. For the high inclination, like more than 60 degrees, we can see almost nothing. Okay, there is in comparison with this, it's the same unit, so you can compare the 10 degrees and 80, even at 70. That's just a black image. This is a very new thing we did here. Is spectra of puffy disk. We hope it can maybe solve some problems with analytical model which are used now. Most importantly, the puffy disk is the spectra has much lower energy with high inclination, so the difference is 2 orders of magnitude. Here, with lower mass accretion rate, from the free simulations we have the peak is moved to the higher energies. And when we compare it with a thin or slim disk spectra, which is an analytical model used for fitting black holes, spin mass, and other parameters, we see that there is a big big part of the spectra is more energetic and higher energies than for an analytical model. And for this is for inclination 10 degrees, and this is also not different from the analytical model. The energy is lower, but for high inclination of 70 degrees, which is this curve, the energy is much lower and shifted to the right. This is without quantumization, and we do look the same and include the quantumization in the process. The difference is even higher. This is the big the spectra is very different from an analytical model. Okay, so the puffy disk is a new type of accretion disk which results from numerical simulations, not from an analytical model. We hope that it brings us a more realistic view on accretion than a 1D model. Also, we know that we need a strong magnetic field to stabilize the disk, and the spectral properties will be different than an analytical model. We published our first paper in October in APJ Letters, and if you are interested, you can find it.
Questions about puffy disks?
Yeah. So the nice thing about thin disks is that you can figure out the radiative efficiency simply from the ISCO. And it looked like some of your plots, the integral over the frequencies would give you a different radiative efficiency. So how can you elaborate on what kind of radiative? So most of the emission is not coming close to the ISCO necessarily, or
most of the radiation is coming from close to the ISCO.
Close to the ISCO, but it depends on inclination as to whether you see that part. Right?
Yes.
So
yes.
What is did you plot the radiative efficiency versus? inclination or something else?
I didn't. It's a good idea to do. Oleg did in his paper in 2016. He did analysis of efficiency. He said it's higher than a thin disk.
Higher.
Higher. And also from, but I'm not sure how he did it actually. For if he calculated the spectra or if he just look at the heating cooling rate.
But I would expect the thin disk to have the highest radiative efficiency simply because you get all the radiation out. The disk cools, and here you have a puffy. Some of the energy is trapped with the material going into the black hole.
787
So
puffy.
So is also there like in the spectra Ramesh computer there were the processes of radiation transfer of atomizations in quantum Bremsstrahlung which can increase the total energy. I'm actually not.
But Ramesh, wouldn't the energy be the most energy you can get out is the gravitational energy, right? And in a thin disk, you would expect all of it to go out. So this must be lower efficiency.
For
It
the
is,
given
yes.
m dot, it should be, yes.
It should be.
Yes, it is. Of course, efficiencies in accretion disk business is sometimes defined differently.
Well, it's
But the efficiency you have in mind,
total luminosity over
yes,
m dot
exactly.
system.
The efficiency you have in mind is lower. And what you said about the maximal efficiency for thin disk is of course correct, fundamentally correct. So this, everything which is not exactly thin disk with the inner edge at ISCO with zero torque boundary condition has lower efficiency than this fundamental Shakura-Sunyaev.
Right.
So puffy disks in this very sense have lower efficiency than Shakura-Sunyaev.
Mm-hmm.
Are there any other questions? Ramesh?
So, Debora, you showed this super Keplerian, which I had forgotten, even though I'm on the paper. So, you showed the zone, which is super Keplerian, and it seems to include both the puffy region
Yes.
and the high density region. So, is there any difference between these two in terms of super Keplerian or omega or anything dynamically?
So if you what is it? Okay, if I show you the photons again, the whole plot is
Yeah.
so the colors is is the omega over omega Keplerian. So most of the puffy region is actually Keplerian.
Keplerian, right. And this region is super
Super
Keplerian.
Keplerian. Yes.
Okay. So the main difference in the puffy region is that there is more radial velocity,
Yes.
but the angular velocity is pretty much the same.
Okay, if there are no more questions, then let's thank the speaker. And Peter, I heard your question about M87, so let me tell you that this is the opposite corner of the parameter space. M87 is optically thin, which makes it, well, for some reasons, more simple to simulate because you don't have to bother that much with the radiation interaction with gas. And on the other hand, it's optically, geometrically thick. So it's for two reasons why M87 is easier to simulate, because it's geometrically thick. Your grid doesn't have to be that fine. So this is really difficult in comparison.
Right. Is there reason to think that there's some other black holes that are like this?
We expect a lot of X-ray binaries to be corresponding to this model of accretion.
Probably most quasars.
Right, so we'll have our second talk by Bhupendra Mishra. Bhupendra was a PhD student in Copernicus Center in Warsaw at the same time when I was a common visitor there. And currently he's a postdoc at University of Boulder. And he's an expert in GRMHD, and he will tell us a little bit about strongly magnetized accretion. And we never did a project together until yesterday. We started working on a project yesterday.
Yeah, so thanks, Matt. That's really Nice of you. Thanks for inviting, and very nice to interact with all the people here actually. So I think it's a really golden era for we people working on accretion physics, because EHT results are coming, LIGO results are coming, lots of tidal disruption event data is coming. It's like best time to understand the accretion disks from all the angles you want, like whether these are strongly magnetized disks, how they circularize, how they puff up, or how they elevate. Everything you can learn from, say, numerical models, which is like really developing supercomputing facility, like GPUs are coming and accelerators are coming. So it's a really golden time to understand these accretion disks. Still, there are few challenges, like I would briefly talk about them. And as Debora was talking, that standard disk models are suffering with lots of instabilities. The 3 or 4 actually I'm going to talk about. And we are going to say, after like in next few years, it's going to be established that strongly magnetized disks are the need to stabilize these instabilities. So we are getting into a conclusion like in next few years. Just to briefly mention what kind of accretion disks we are talking about. So imagine there's a black hole there, there's some companion here, it's a low mass black hole X-ray binary. You have a accretion from the companion, it forms accretion disk. Occasionally it would show some jets, and jets might be appearing and disappearing depending on the spectral state, because these disks are jumping from one spectral state to the another spectral state. So it's very interesting that what's happening in this very inner part, we can try to simulate that. The one thing which is really challenging to understand, what type of magnetic field is going into the disk and how does it get amplified. So that's the open question, and we see it with different types of magnetic field in our models. Like Debora was simulating with, say, this quadrupolar field configuration. We came up with, say, vertical field, different people come with, say, different
Why do we
polarity
need to
fields.
come up with this? In principle, it's the field coming from the star, isn't it?
That's right. So in the global simulations, we are not able to fit the entire system. We are able to simulate what's happening very close to the black hole.
In principle, you can zoom on the part that fits the disk and see what the magnetic field does.
Right. So then there is a time scale problem. Like we are not able to fit the companion and the simulation domain. There is an effort going on currently in UCSB that injecting a stream from outer boundary with, say, toroidal or radial magnetic field configuration, and seeing how can it circularize and form the disk, and then what magnetic field strength will develop, what kind of topology is developing there. So still it's challenging to fit both of them together in a single computational setup.
Is the star spinning? I mean, is that what's called? So the magnetic field comes from the star towards the. So
Well, there is a tidal force that brings the field into, so that the star is deformed, and some of the stuff goes into the companion. Which
so
is
you don't. It doesn't require the star to be spinning. No.
No, I mean, it could be, but
Yeah. So there are some challenges, like there are different ways you can approach this problem. One is like you can do pen paper calculations, which Marek is going to do after this talk. And these has been really useful to understand the simulations and sometimes observations also, because you cannot just rely on a simulation until you confirm it from some sort of analytical calculations or theoretical model. We are using Prometheus also, like it's a big supercomputer in Poland. It's really helpful to have that. And then you can compare your simulations with observations. So these are different models which are popular over the last few decades. We are going to say that geometrically thin disks are unstable. The other class is slim disks, which are also optically thick, but geometrically slightly thicker than the thin disk, but they are advection dominated. And these are geometrically thick disks, which are probably in M87, and these are also called Polish donut models. And, yeah. So what's happening actually in the very inner part of Shakuratsu-Nair disk model, that there are 3 different regions. The innermost one is radius and pressure dominated, and soon after this paper came out on the Shakuratsu-Nair disk model, they found that it's thermally unstable. And it means that the heating rate will dominate over the cooling rate. At that time it was not very clear. It could be heating rate dominating over cooling rate or cooling rate dominating over heating rate, and the disk will either evaporate or collapse. So this was going through the thermal instability, and it was also suffering from viscous instability, which is like the disk was fragmenting into rings due to negative diffusion coefficient, that the density, it was forming clumps of high density regions. So this is suffering from both instabilities. And in the rest of my talk, actually, Debora was talking about, so there might be slight difference that Rg, I defined it at gm over c squared, and that's unit of length, and unit of time will be Rg over c.
So one thing that I don't understand is if the heating dominates, you just puff it up a little bit, if the cooling dominates, it becomes thinner. Why would it collapse or be not as stable?
So it's an unstable system. It's not a...
There's no feedback.
May I comment on this quickly? It is not only heating dominating over cooling, but it is the question whether in this heated, overheated version, disk is expanding or not. So it is dq/dh plus greater than dq minus, which is plus is for heating over dh. So when the disk is expanding and it is when expanded even more overheated, then there is instability. And the same when it is overcooled and is more even when it is collapsed. Because otherwise, of course, it will be established thermal instability. Yes, so it is dq/dh, and that was what C.P. Rao found.
Thanks, man. So, as the previous question, so these simulations are really expensive. So, we are trying to do small simulation domains. So this one is like a cylindrical wedge. We did this first simulation, which is a radiation pressure dominated, geometrically thin GRMHD simulation. So this is a cylindrical grid system here. That we used a periodic boundary condition because we are not doing an entire 360 degree. This was before like 3 years, so we did a smaller simulation. Inner boundaries are outflows, top boundaries are also outflows. We are supplying constantly some matter from the outer boundary. It's a constant boundary condition. So we see that with some magnetic field, we used a small poloidal loops of magnetic field confined within the disk. And what you are seeing here, that the disk initially was getting thicker. That's where the heating was triggering due to the local MRI, like the local heating, which is like due to say MRI, and it was puffing up. But it couldn't do that much longer because the cooling dominated and this disk started to collapse. So coming back to your question, if it was actually an unstable system which was going in the say evaporating phase, it could have just went the other way around. So, yeah. So this is the similar thing to see in a more appropriate plot here. So this is time, this is radius, and this black dashed curve is showing the local orbital period at the time where the MRI triggers and probably the heating starts. And this was getting slightly thicker, but this is like a thermal time scale where the local cooling like dominated and the disk collapsed. So this was height profile, that it initially got thicker, then it got thinner and collapsed to a single zone that we cannot resolve it further. So we stopped the simulation there. And the right panel is, because we did two set of simulations because we couldn't rely on one resolution. We wanted to test if it's valid for high resolution or not. So this is what happens, that if you take the ratio of heating rate to the cooling rate, this is again time, this is radius, the cooling rate is dominating over the heating rate. We certainly don't trust what happened after that because the disk is not resolved, it has collapsed to one cell. So the cooling rate dominates over the heating rate, the disk is collapsing, thermally unstable. And the region it's happening is from classical astrophysical accretion disk model. So this is a famous equilibrium curve, which is like called S curve. So I'm showing just two branches here. There is another branch on top, which will be slim disks or advection dominated accretion flows. You can also put your M87 disk somewhere on the other corner here. So what we are saying that this is an unstable branch, and this is where the radiation pressure dominated region falls, and this is gas pressure dominated branch. We started the simulation somewhere here, and it started to collapse. So again, this is a plot at a fixed radii for a fixed value of alpha, which we got from the GRMHD simulation. Because a priori you cannot say any value of alpha. So the philosophical question is, how will you start a Shakura-Simnay model in your numerical setup? Because you need an alpha value to start the simulation. So that's like a puzzle, that where will you start your simulation? Because this plot can be only plotted if you know alpha. So we followed these simulations with a series of about 6 or even more 2D viscous hydro simulations to see what happens where you initialize the setup and where does it fall at the end. So it's all of them are just falling into the stable, towards the stable gas pressure dominated branch. So we have understood, based on previous some local shearing box simulations, these global simulations, that Shakura-Simnay model is thermally unstable. So we need to figure out some new model or figure out how to stabilize them. And the magnetic fields seem a possible way to do that. Like similar plot Debora was showing, this is Oleg's, from Oleg's paper. So Oleg first time did a global simulation with a magnetic field configuration, which showed that the disk can get thermally stable. The idea was that you put quadrupole field configuration and you get a larger radial component of magnetic field in the disk. And when you in a Keplerian disk, or when you have a shear in the phi direction, you are stretching it and then stretching it and creating more of a toroidal field, and that helps to stabilize this radiation pressure dominated disk. So this was a Oleg simulation. We did it in a different magnetic field configuration. So we did 4 simulations total. So each simulation was like 6 million CPU hours for this particular high resolution. We had mesh refinement to maximally resolve the disk in a fully 3D global system. So the grid resolution was 2048 times 512 times 1024. This is best we could do, and I think Mathiliska is coming up with a better resolution, but this is what best we can do with CPUs, not with GPUs. So what we are interested in is this particular region, which is strongly magnetized. These are the weakly magnetized flows, which people have been studying earlier. This one is where Ramesh has been working intensively on magnetically arrested disk. These are at even stronger field regime. So when we did these simulations, we are finding something very different from what has been thought, somewhat similar to what Debora has been talking about, that the disks are getting puffy, or we called it, so actually these papers came out 1 week of time gap. We called them elevated, and you guys call them puffy. So, but the idea is that the disks are not remaining thin the way you start with. They get either puffy or elevated. The disk doesn't want to remain thin, it's getting thicker. The accretion is happening through the upper surface layers. So this is showing the velocity profile, phi averaged in like a vertical slice here. So you're seeing that the magnetic field pinches and the accretion is happening on the surface layers of the disk. There are weak outflows at the midplane, which we are trying to understand, are they real or a numerical artifact? So that's open question currently. And these are simulations which are started with, say, initial different beta, like 1000, 300, 100. So that's like initially what ratio of gas to magnetic pressure you have with the net vertical field. So we start with, say, 1000, it ends up to 100. We start with 300, it ends up like 10, or 100 will end up here. So the whole idea is that what could produce more magnetic field strength in these simulations. So the toroidal field has a large radial component which was being dragged, producing lots of B phi. Here we are having a large colloidal field which is being dragged and producing significant radial component due to the accretion, and then a significant B5. So these both simulations are actually advocating towards some sort of elevated disks or puffy disk simulations. The one really striking thing was we were comparing our global simulations because they were high resolution with local shearing box simulations, because we were approaching towards really high enough resolution that we can compare with the local shearing box simulations. So these triangles are from a local shearing box simulation, which are also started with the net vertical field, and these black squares are from our simulations, and the one where it's normalized with the gas pressure, one with normalized with the magnetic pressure. And we are finding that they are coinciding with each other, and a slope of 0.65 is found. Actually, that was predicted from local shearing box simulations. And if you take the ratio with respect to gas magnetic pressure, it's a horizontal line. So this one is a total alpha. Just to make it clear that we are not, this one is not showing the just turbulent component. It's a total alpha, which is primarily Maxwell stress dominated, but not just turbulent, the total Maxwell stress. You can then decompose the total Maxwell stress into coherent component and turbulent component. So the Shakura-Shinnev alpha is actually turbulent alpha component. And this was from the global GRMHD simulations we did. So that was also computed similarly, but you're saying it was like 0.02. That was with zero net flux simulation. And if you seed it with the strong vertical fields, the alpha is really increasing a lot. So you're producing large values of alpha. Another very interesting feature which has been seen briefly in MAD disks was spiral structures. So in Mark Avara's paper in 2015 or something, they found that the disk was showing a spiral structure. So it could be that we see in nature that nature picks spiral structures. So maybe around the black holes you have some spiral structures. They could explain probably some variability features in the future. And when we try to quantify them, so this is an animation, I should forward it quickly to see the final spiral structures. So this is an equatorial slice where you are seeing the evolution of mass density for the beta of 100 case. So you're seeing that there's a density contrast of sometimes factor of 5, sometimes even an order of magnitude, and these spiral structures are being formed. And very striking feature is that if you try to see that in the magnetic field configuration, so this is plotting, I'm plotting the B phi here on this layer which was accreting in, the blue part in this radial velocity part. So it's always in theta, you're seeing that there's a flip of magnetic field sign at different places, and if you try to fit that spiral structure, it can be fitted with a logarithmic spiral, and the exponent here is inversely proportional to beta. Like if you are getting the stronger and stronger magnetic field, the beta will get weaker. So the B will get smaller. And we are further investigating it and trying to apply for aging variability and other things. So this happens only when you are getting very strong magnetic field, a beta of 100 or beta of 50. And just to compare, quite similar results here. You are seeing that the Debora et al. Simulations, and we are finding the similar surface accretions or dominant accretion on this surface of the accretion disk, and Debora didn't find weak outflows, so that's a difference between these two simulations. We are finding the mid-plane is weak outflow in our simulations. So where are we heading to with these kind of experiments? So Mitch came up with the idea that how can we explain the spectral state transitions in black hole X-ray binaries. So if you are probably familiar, there is a strange pattern in low mass black hole X-ray binaries that they are jumping from oftentimes high soft state, which means the X-rays are in soft but the luminosity is high, and these are where the geometrically thin disks are lying. And this is like a quiescence, and then your luminosity is increasing, and this is called jet line because you only see the jet in this part, and once you go to geometrically thin disks, the jets are generally turned off. So an open question is to understand the jet physics probably and also the spectral state transition. What happens if somehow we can explain this with some magnetic field development there in the very inner part? So the idea of this particular model was, it's an analytical model. We are trying to do that in a numerical simulation. We haven't got it working yet. So the idea is that if there is a magnetic field configuration in the very inner part, so I didn't mention that geometrically thick flows are advection dominated, and then they are prone to advect the magnetic field efficiently. Thin disks will tend to diffuse the magnetic field outwards. So if there is a loop of magnetic field which got into the transition region, the inner part is going to be advected, the outer part is going to be diffused out, and you are generating a single polarity large scale magnetic field in the very inner part, and that could just constantly develop and make the disk more puffy and eventually probably lead to a state transition and also explain probably the jet production because it requires large scale colloidal flux there. So this is where we are trying to head using these simulations of accretion physics. To summarize, probably we are going to replace geometrically thin disk model with puffy or elevated disk models. We may not expect 8,000 citations like secretion model. So the strong fields stabilizing the various instability we have been seeing in say X-ray binaries, or also say gravitational instability, which was in say Asian context where the question is the mass accretion was not happening because the disk was fragmenting into gravitational instability. Yeah, so that was pretty much all from elevated disks. Thank you.
Questions to Bhupendra?
So about half a year ago, we had a talk by Omer Blaze. He's doing simulations with the radiation included, and he's finding that the upper layer above the disk is dominated by radiative viscosity, actually. I was wondering, I mean, your simulations do not include such an effect, right?
So we have not included the radiation in these ones. We are including it in the next simulations.
Because it could make a difference
Yeah.
for the geometry.
So that was the whole idea, that we turned off the radiation first to see MHD effects, and then turn on the radiation to separate them out, that what was creating that difference. So I'm following these simulations with a better boundary condition, which is like say having GR, like a real black hole, and then adding the radiation.
So Oleg, when he did his work, his result was, if you have a quadrupolar field geometry, then the disk is stabilized. But with a dipolar geometry, it was not stabilized, is what I remember. Now, in your simulations, you're starting with this vertical field, which is like a dipolar field, and you are getting a stable configuration. So do you understand this difference between what you are finding and what Oleg was finding?
So one main difference I think is that when Oleg simulation, it was a very weak, it was first of all non-zero, it was zero net colloidal flux, so the loops were closed, so they were not having a large colloidal field which can be stretched and produce a large toroidal field. And these simulations are having a large colloidal flux where the magnetic field lines are hinged on the boundaries, and they are always there to give us significant drag in phi and produce b phi. So that's one big difference, because in Oleg simulation it's a colloidal field which confined within the torus. So it's a weak, initial weak colloidal field. Here we are giving a large colloidal flux here, initially.
Yeah, but your beta 300 simulation, that's a fairly weak field, right?
Beta like 1 or 10.
So that's a big difference in the zero net flux and non-zero net flux, that even with the strong magnetic field with zero net flux, you can like you wouldn't stabilize the disk certainly, but if you have a weaker field but a larger poloidal flux with non-zero net flux, you can produce large toroidal fields.
Okay.
I think that's the scenario.
Right.
And it will
But
be
this
more.
is kind of less natural, right? Especially if you say you're going to pin it at the boundaries. That doesn't look very natural to me for a real system.
So it's still unclear actually what will be in the real system, but even in the Rochelow overflow, most probably the star has a dipolar field. It would initially have some large poloidal field which is going to be dragged with the stream and then circularize.
Sure. That will look like Oleg's setup,
Right,
not
to
your setup, because your setup has got lines going
Mhm.
off in the z direction.
Right.
Anyway, yeah,
Yeah.
we'll talk about that later.
But once we add the radiation, that would be more clear if are they really going to stabilize, or because radiation is important to say about thermal instability.
Mhm.
There are no more questions. I will ask a question. With setting up toroidal initial magnetic field, why is that not a right way to do it?
We are doing that actually. You mean initializing with toroidal field?
Pure toroidal
Yeah.
field.
That's a reasonable initial good configuration, because in tidal disruption events that could be really a possible way to initialize toroidal field. And yeah, I think we are following that with a grad student in our group.
So, and also the comment, like elevated discs, come on, be creative. Puffy discs, so much better name. I'm joking, elevated discs are
So I think once we add the radiation, so radiation can create puffiness, but magnetic field can just
Oh,
elevate.
okay, so that's the, okay, with radiation it will be elevated puffy.
Yeah.
Perfect.
Because magnetic
I'm very
field can,
happy.
yeah.
Okay, so it's thank you, Bhupendra, again.
Thank you.
And our final speaker today is Marek Abramowicz, who was brought up in was two previous talks quite many times. Marek is in this business for like 50 years, I think. Sorry for this remark, Marko. And was responsible for many important developments throughout the years in the theory of accretion, including developing this slim disk model. And apart from that, Marek is my scientific mentor and a person who convinced me that instead of doing signal processing in industry or in military, I do want to study accretion. So thanks, Marek.
That's where the big money is. Accretion is, right?
So that will be a blackboard talk, and for that reason we need to rotate 90 degrees our seats. And Fabio will set up the camera.
If I sit here, will I be in the way?
Just trying to understand how we're going to do this.
Maybe I should be back that way.
Yeah, maybe it's better though.
So my talk is announced like all talks on this flash screen, and some of you may notice that I am either Marek Abramowicz from Arizona University or Marek Abramowicz from Chalmers University in Göteborg. So if you notice this, you might wonder where I am from. I'm neither from Arizona nor from Göteborg. I actually live in the same piece of Europe which Debora. Oh no, Papa is sorry.
This side of the line.
Unelected We tried to do
You try to annex, yeah.
We Poles.
Did it for some
But Opava is actually here.
That's all right.
In the Czech Republic, that is Poland. And that is a beautiful countryside where I live, in a small village. Gierałtów. Okay? I'm saying where I live because not very far, about 15 miles from Gierałtów, there is another village called Krajanów. So that is Gierałtów, that is Krajanów, very close, where Olga Tokarczuk, who got Nobel Prize in Literature this year, lives. And she's my neighbor and a very good friend of mine. So I will take this opportunity to tell you that in the local book store, Co-op, you can buy her, to me, best novel translated to English, Flights. And I brought also another book of her, which was not translated to any language, except it is written in original Polish, Zagubiona Dusza, The Lost Soul. And there is a very interesting cosmological hypothesis. There's a book for children, and it got last year Bologna Ragazzi Award, which is very prestigious in this field. So Olga says that we are losing our souls because our souls were created at the beginning of the universe when the universe was expanding slowly. That is in her words. Therefore, if people, some of people, are going from Arizona to Göteborg to Harvard and they are moving fast, the souls cannot catch up, and we are losing our souls. A beautiful book, not translated, unfortunately.
You can pick them up afterwards.
To English, but it's very, very short, so this, Flights. And I will be talking today about puzzles. I'm working with colleagues on things which are connected to LIGO Virgo and to Event Horizon Telescope, and we are kind of confused by things which seem to be pretty elementary. And I would like to talk about these confusions and puzzles and why I do not understand this. Maybe answers are simple. And because I'm talking about simple things, I will start from something which is really simple. Euclidean three-dimensional space, point, and light trajectory, which is of course a straight line. So light is moving with velocity c, and it is any point. You take the shortest approach to this line and you call it R star. Okay? So then, of course, the angular momentum with respect to this point measured at this closest approach is L R star times C. You can square it, and then you may say that L squared over R star squared is C squared. And this C squared is a proxy in Newton's theory for energy square. Okay? And then you have a formula which explains what is the effective potential for the photon motion. You have energy A square equal R square over R square. And of course, that is this hyperbola. So I'm plotting effective potential. And if energy is this, that is the shortest approach. Okay, that's effective potential in kind of Newton's theory, and also in Minkowski space. Now I will make this point that if I have a spherical matter distribution, then at the center of spherical matter distribution, space-time is locally Minkowski. And of course it comes from a remark of Isaac Newton himself, that inside a shell of matter in any point, there is no gravity. And there is no gravity because if we if we take a piece like this, here and there, then the distances are 2 square, but the amount of mass, if the shell has uniform density, is proportional to R square, and then the two forces cancel and there is no gravity. And if we take now the most general case in Einstein's theory of gravity, static, spherically symmetric space-time, then we may write for a light trajectory that 0 is ui, uk, jik. And because I will take coordinates which are diagonal, which is always possible in with spherical symmetry, and take into account the well-known fact that trajectories of particles and photons are planar in spherical symmetry, always. So I, for simplicity, take the plane, equatorial, so-called equatorial plane. Theta is in spherical coordinates fixed, so there would be no theta component, only u phi, ut, and ur component, and it is then 0 equal ut square gpt plus u phi square g phi phi plus, look what I'm doing here, this index is up, GRR, and I can do it because the metric is diagonal. So if I put this on the other side, it would be minus GR UR square equals, that is energy, that is angular momentum, so it is energy squared g phi phi plus GTT, thank you, g phi phi, and this quantity is by construction greater than 0 because I'm using the signature plus and 3 minuses.
Why are you doing that?
Sorry?
We all grew up with the opposite convention.
No.
You are from a different generation.
No, I'm not from different generation, although that was very kind of carefully said. I'm not from a different generation. I'm from a different textbook, Ramesh. I'm Landau Lifshitz.
It's the same in Italy. I'm a different generation.
Oh no, it's terrible, yeah.
But Paula,
but you have Marek student anyway.
Paula was my student, so I told her,
You probably learned
use
it from,
Landau Lifshitz.
and you learned it from Krautmann.
What are they teaching you in second grade, Julia?
Anyway, that's the
Okay, that's what you're going to do, okay.
So that is greater than 0, and therefore E squared greater than, there would be a minus L squared over R tilde squared, where this R tilde squared is equal G5 phi, no sorry, yes, G5 phi over GP. Okay, so it looks like Newton's formula or Minkowski formula, but there is this GTT. And in particular, in vacuum Schwarzschild metric, which is written on the bottle in this painting here. There is a painting? Yes, here. You see there is a Schwarzschild metric on this bottle. So it means that I don't need to remind the metric. This function in Schwarzschild geometry has this shape. There is a maximum at 3n, and that is horizon here at 2n. So that would be the closest approach. That of course is for
Saying it at some point.
yes, that is for some angular momentum. Okay, so it's not a general that corresponds to some angular momentum, but for a different angular momentum, this maximum is in the same place that would be, and asymptotic is zero. Okay. And then, if we have, it would be less. It would be kind of better if there is only one curve. So if I had a pair, if I had a photon, which is characterized by energy and angular momentum, in the sense which I explained, that is the closest approach, and it is kind of a trajectory of this photon. If it is emitted here by some astrophysical source, what it is doing, kind of returning to us, maybe from a different direction, but it is returning to us. On the other hand, these photons, which correspond to this particular pair, are lost. We will never see them. They are lost in the black hole. Okay. And what is a trivial remark, however trivial but important to make here, is that we never see photons which were emitted or touch, not only emitted but touch anything which is smaller in radius than 3m. These photons which we see are never, because of course we see photons, direct photons, emitted by say this puffy disk or whatever this was discussed before. We never see photons which were at any time closer than 3M. And that is obvious, but not often said. So my two colleagues, Jean-Pierre Lasota and Wodek Kluźniak and I, decided that we will write a paper which we wrote saying that using electromagnetic radiation we cannot test the existence of the event horizon. That is a theorem, okay? And that is in this sense. So then I will not be talking about photons moving in vacuum Schwarzschild because of course it is very well known textbook stuff.
Before you move on, just a question. Yes. So if you have a flashlight and you put the flashlight at 2.5 M and point it outwards, wouldn't the photon be able to escape?
Some photon, yes. Some photon, no.
Right, so there could be photons.
No, look, I was actually careful saying things. That is the astrophysical source of photon.
But if you put it inside...
Yeah, of course, you are right. Yes. So then the question, very, very good that you said this. The question is, could we have something which will beat this thing? A flashlight or something else, or some compact object. So really my talk is that, okay, we had here this maximum. But then closer in, not necessarily horizon, but at some location we will match this metric with something else. Okay? So because it is very difficult to have a flashlight inside the 3M horizon, and the reason for this is that it is very energetically expensive. For the reason that for orbits, for circular orbits, I'm talking only about circular orbits now for simplicity, but that is a general argument. For circular orbits, the centrifugal effect, that you write the formula for acceleration, and there would be a term which is proportional to v squared, orbital velocity square, points in the same direction as the gravity. So the fastest you go on an orbit which is radius smaller than 3M, the stronger you pushed in. So moving around will not be a good idea to have a flashlight there. It must be an engine pushing radially, and that is enormously expensive. Okay? So of course we may construct this if we have enough money, but the question is, maybe nature is doing something. Okay? So it looks like a black hole, but closer in, where it would be a black hole-ish horizon, there is something else. And of course the first thing which comes to mind is some very compact object. Okay? So compact object here is matter, spherical. So then, because it's vacuum, then it is Berkov's theorem, which says that if it is vacuum and spherical symmetry, then it is Schwarzschild. There cannot be anything else. So the run of this potential is the same. But then, of course, here it is not vacuum. It's a material source, and depending on equation of state, metric could be very complicated, and we don't know a general formula for a metric for accompanying object.
By the way, this is not hypothetical because a neutron star with two solar masses has a Schwarzschild radius of 6 kilometers. What do we know?
There are no
6 kilometers, the Schwarzschild radius, and we know that the radii of neutron stars are of all the 12 kilometers, so it's 2 Schwarzschild radii.
Yes, but I need
you need
1.5.
1.5, so I'm saying.
That's the whole difference.
But if you have a two solar mass neutron star, you're getting pretty close to that.
No. Yes, pretty close, but that's the whole point. Topology. You are either here or there. If you are there, there are no neutron stars known to me. Boson stars are compact enough, but not neutron stars. Whatever is the equation. That's kind of not important whether there are neutron stars or not, because I'm talking about anything. Okay? And this anything surely effective potential here is like in Minkowski, because at r equals 0 we have locally Minkowski spacetime. So it must be whatever it is, neutron star or boson star or Grava star, whatever, if it is material and spherical, it must be like this. And then of course it may have bumps, but generally it is like this. Okay. So then first of all, photons are, if it is transparent, and even if it is not transparent to photons, it will be transparent to gravitational waves, because, okay. But then, there are these trapped orbits. Okay, so there is one possibility, that we have something material with the radius less than 3m, and then we have, that is the topology, general topology. By the way, Grava stars, of course, have this potential, but the topology is the same, but it is extremely steep. It is like this. Okay? And then it goes very, very high.
So if you have gravity waves, they oscillate in this trough?
Yes, that's the point. But that is possibility number 1. And possibility number 2 is this, that on the other side, here, there is no material source, but there is a vacuum. And for example, what we can do is we can take Schwarzschild, cut it here, and then paste 2 halves together. That is a construction of the simplest wormhole. And in this case, there are now 2 infinities. So that is a second. Mr. Chairman, do I have still time to go?
Well, you have 6 minutes.
6 minutes?
A lot.
Okay. So I will not tell about this, and for the reason that I have only 6 minutes. And the second reason is that we have something to say, which I think is very interesting, because it may be used in the discussion of event horizon and telescope images. But it is very new. That is less new. That is 2 days, and that is 2 months. Okay. And here we haven't completed all the calculations, although we know the result. Here we completed all the calculations. So there is a solution of a compact star which was found by Schwarzschild himself, and it is called internal Schwarzschild solution, and it is a star with constant density. And the metric for such a star can be written down it's a spherical metric in this particular form. That is like GTT, and taking this GTT out, and that is the space. But space, because I took this out, kind of conformally adjusted geometry. A good reason for doing this is that in static spacetimes, dt is extremized for photon motion. If we send a photon from point to point, then on the null geodesic, in static spacetime only, the time needed to complete the pass is minimal. That is Fermat principle. So if I know that this is 0, and because on the photon pass the S is equal 0, I know also that is equal 0. So the null geodesics projections on the tree space are geodesics. That's simple consequence of this conformal rescale. And then the view.
Is that what you call optical geometry?
Yes, that is why it is called optical geometry. And the reason that I am talking about in this context is that this Schwarzschild geometry for rho equal constant matter is in optical geometry spherical. Okay. So we know immediately, because that is a sphere, that light goes on all kind of these trajectories. Not only we know that if this is a kind of a wave, then the wavelengths depends on the number of nodes along the path. And we know immediately, because we, in Schwarzschild geometry, that's a constant, which depends only on the mass and the place and the radius of this star. Okay. Oh, sorry, that is important. power. And that is a kind of a monotonic function of an R, which is scaling, which is not important. So we know the lengths here analytically, and therefore we immediately know the wavelengths, and immediately we know the frequency. And these frequencies are frequencies of the normal weakly damped normal modes oscillations which were found in rho equal constant neutron stars years ago, not 50 years ago, but some 30 years ago, by Chandrasekhar and Valeria Ferrari, numerically. Okay. And these are trapped gravitational waves. Then, of course, they are weakly damped because there is opening. These waves are slowly leaking from this spherical container. And if we say, okay, let us use black body estimate, how quickly they will be leaking. So one may say this, that energy density, if it is black body, would be 4 sigma c t to the fourth, and flux of radiation from this little hole is F, which is sigma to the fourth, and then the total energy is E times 4 3 pi a cube, and here the total loss of power is this times the surface, and then of course the damping time is this divided by that. But this we know analytically, and therefore we know the damping time analytically. And it's obvious that the power here, that is compactness, which by the way you see that cannot be greater than this, that is so-called boundary limit, and there are beautiful things connected to this. But anyway, we know it analytically from this black body analogy. Of course, there is an equation which describes these modes and their damping, so-called Tucholsky equation, which people in gravitational wave business are using when they are calculating gravitational waves from oscillations. And Chandrasekhar and Ferrari, 30 years ago, were unable to solve these equations analytically, and they solved them numerically. Ilka Horak, a young professor from Charles University Prague, is a mathematical genius, and he solved analytically in the paper which we will submit. And yes, it's Ilka. That is the only known event in the history, Ramesh, when something was done by Chandrasekhar numerically and then by somebody else analytically.
Wow.
Okay. So we have
Chandrasekhar was pretty old by that time. He was 80 plus.
Yes, he was old. Yes, he was very old. But full of energy. I was visiting him at the time in Chicago. And he was very proud of this work with Valeria, and also was proud that he is working with Valeria. for reasons which I will tell you at the Christmas party. Anyhow, so there are there are these gravitational wave modes, which the so there is some function, and then in terms of time it is like this. So the real part of sigma is this frequency which we estimated here by this optical geometry trick. And let me write that is equal omega, and I will put here exclamation mark, because solving this equation and using this simple, no single line of calculation really gives the same result. Okay, so it is like omega here for different ends. Solution of I haven't wrote this equation. That is kind of a like Schrödinger equation in shape, and optical geometry gives the same thing. And then that is the solution of equation, and this black body is not flat. Has this slope which I said -3/2 different. And the question which Ilka and I, sometimes with other colleagues, they are discussing for the last few months is why there is a difference. Okay? And we don't know. But I tell you something which is probably a very stupid idea. Black body estimates, a simple black body estimate is a quantum estimate, because both energy density and energy flux are derived from quantum mechanics. And of course there is a Planck constant in this Stefan Boltzmann constant. That is a quantum object. While I said that the equation for gravitational waves looks like Schrödinger equation, but it has no Planck constant. It is a classical equation. If the difference between these two approaches is really connected to quantum mechanics, then it's something very great, but that is only kind of a stupid hope. We don't know. It's probably not quantum, but there is a possibility that it is. But there is a classical application of this, and this is, and I'm addressing this to Paula, resonances. These frequencies are always a whole number times a function, and this function is the same for all modes. So these modes, ratios of them, ratio of frequencies of the modes, are ratio of natural numbers. That, of course, is the necessary condition for a resonance. Not sufficient, however. And sufficient conditions are complicated, as we know. However, there is this possibility that in this ultra-compact object, trapped weakly damped gravitational waves could be in resonances, and that is what we are working on. Yeah, I know. And I said nothing, I'm very sorry about this Reisner-Nordstrom wormhole, which is a new excitement.
You'll have to come back.
Thank you.